Colloids and colloidal sols. The various substances which form colloidal sols are divided into two categories named lyophilic and lyophobic. If water is in dispersion medium, the term used are hydrophilic or hydrophobic. Number 1. Like lyophilic colloids. The word lyophilic means liquid loving substance like gum, gelatins, starch, rubber, which when mixed with a suitable liquid as the dispersion medium directly form the colloidal sol are called lyophilic, and the sol thus obtained are called lyophilic sols. As they form the colloidal sol directly, they are also called intrinsic colloids. An important characteristic of these sols is that if the dispersed phase is separated from the dispersion medium, say by evaporation, the sol can be made again by simply remixing with the dispersion medium. That is why these sols are also called reversible sols. Further, these sols are quite stable and can not be easily precipitated. Lyophobic colloids. The word means liquid hating. Substance like metals, their sulfides extra when simply mixed with the dispersion medium do not form the colloidal sol. Their colloidal sol can be prepared only by special method. Such substances are called lyophobic and the sols formed by them are lyophobic sols. As their colloidal solutions have to be prepared by indirect methods, they are also called extrinsic colloids. These sols are readily precipitated or coagulated and hence are not stable. Further, once precipitated, they do not give back the colloidal sol by simply addition of dispersion medium. Hence, these sols are also called irreversible sols. The greater stability of lyophobic colloidal sols then the lyophobic colloidal sol is due to the fact that the former are highly hydrated in the solution. The essential points of difference between lyophilic and lyophobic sols are given in the table. Point of difference between lyophilic and lyophobic sols. Number 1 property ease of preparation. Lyophilic sols prepared easily by direct mixing with liquid dispersion medium. Lyophobic sol cannot be prepared easily directly prepared by some special methods only. Number 2 stability. Lyophobic are quite stable and are not easily precipitated. Lyophobic cells they are easily precipitated by addition of a small amount of suitable electrolyte. Number 3 hydration. Lyophilic sols are highly hydrated. Lyophobic sols are not much hydrated. Number 4 reversible and irreversible nature. Lyophilic sols are reversible in nature. Once precipitated can reform the colloidal sols by simply remixing with the dispersion medium. Lyophobic sols they are irreversible in nature. Once precipitated cannot form the colloidal sols by simple addition of dispersion medium. Nature of substance. Lyophilic sols are usually formed by organic substances like starch, gum, proteins. Lyophobic sols are usually formed by inorganic materials like metals and their sulfides. Number 6 viscosity. Lyophilic sols viscosity is much higher than that of the medium. Lyophobic sols viscosity is also same as that of medium. Number 7 surface tension. Lyophilic sols surface tension is usually lower than that of dispersion medium. Lyophobic sols surface tension is nearly same as that of dispersion medium. Number 8 visibility. These particles are neither visible or detected easily by ultramicroscope in lyophilic sols. Lyophobic sols particle not visible can be easily detected by an ultramicroscope. Number 9 migration in an electric field. Lyophobic soles particle may migrate in either direction or may not migrate at all. Lyophobic soles particle migrate in only one particular direction in an electric field. Multimolecular, macromolecular, and associated colloids. The main characteristic of a colloid is its particle size. When some solid substance is dispersed into a medium in which the solid substance is otherwise insoluble, such that after dispersion the size of solid particle lies in the colloidal range, and the system is called a colloidal dispersion. Exam- Example of colloidal dispersion are gold sol, a colloidal dispersion of As2S3 in water extra. Depending upon how the different substances may have size in the range of colloids, the various type of colloids or colloidal dispersion may be divided into the following three categories. Number 1, multimolecular colloids. When on dissolution, a large number of atoms or smaller molecules of a substance with diameter less than 1 nanometer aggregate together to form species having size in colloidal range. These species thus formed are called multimolecular colloids. The dispersed phase in this type of colloidal system may contain large aggregates of atoms or molecules formed as a result of aggregating properties of dispersed particles. For example, a gold sol may contain particles of various size having several atoms. Sulfur sols consist of particles containing 1,000 or so of acid sulfur molecules. These are held together by van der Waals forces. Macromolecular colloids. When certain substances having big size molecules called macromolecules having large molecular mass are dissolved in a suitable liquid, they form a solution in which the molecule of substance, that is the dispersed particle, having the size in colloidal range. Such substances are called macromolecular colloids. These macromolecular substances are usually polymers with very high molecular masses. Example of naturally occurring macromolecules are starch, cellulose, proteins, enzymes, and gelatin. Example of man-made macromolecules are polyth- polyethylene, nylon, polystyrene, synthetic rubber. As the molecule having large sizes and have dimensions comparable to those of colloidal particles, their dispersion are called macromolecular colloids. Their colloidal solutions are quite stable and reasonable true solution in many respects. Associated colloids. Micelles. The substance which when dissolved in a medium at a low concentration behave as normal strong electrolyte, but at higher concentrations exhibit colloidal state property due to the formation of aggregated particle are associated colloids. The aggregated particles thus formed are called micelles. The formation of micelles take place only above a particular temperature called Kraft temperature (TK) and above particular concentration called critical micelle concentration (CMC). The most common example of associated colloid is that of surface active agents such as soaps, synthetic detergents. For soaps, the CMC is 10 raised to power minus 4 minus 10 raised to power minus 3 mole up to 10 raised to power minus 3 mole. Each micelle contains at least 100 molecules. Mechanism of micelle formation. Let us take the example of soap solution. Soap is sodium salt of higher fatty acid and may be represented as RCOONA. Example sodium citrate. When dissolved in water, it dissolved into RCOO negative and Na positive ions. The RCO negative ions, however, consist of two parts, that is, non-polar long hydrocarbon chain are called tail, which is hydrophobic water repelling, and the polar group COO negative called the head, which is hydrophilic water loving. The RCOO negative ion are therefore present on the surface with their COO group in water, and the hydrocarbon chains are staying away from it and remain at the surface. However, at high concentration, these ions do not remain on the surface but are pulled into bulk of the solution. As a result, at a higher concentration, the RCOO negative ion form an oily aggregate with their hydrocarbon chains represented by wavy lines pointing toward the center, and the COO negative part outwards as shown above. An aggregate thus formed is known as ionic micelle. Each of these micelles may contain up to 100 ions. Similarly, in case of detergents, sodium lauryl sulfate CH3CH2 power 11 SO4 negative Na positive. Thus, group SO4 2 negative along with the hydrocarbon chain. Hence, the mechanism of micelle formation is similar to the soaps. It is interesting to add here that at CMC, micelles are almost spherical at concentration highly slightly higher than but close to CMC. They form flattened spheres. At a still higher concentration, they form extended parallel sheets 2 molecule thick. These are called lamellar micelles. It was shown for the first time by MC Bain 1913 by X-ray analysis the existence of plate-like micelles of soaps. Hence, they are named as MC Bain micelles. The comparison of main characteristic of above three colloids are given below. Multimolecular colloids, macromolecular colloids, and associated colloids. Number 1 point. Multimolecular colloids are formed by aggregation of a large number of atoms or molecules which generally have diameters less than 1 nanometer. Example salts of golds, sulfur. Macromolecular colloids are molecules of large size, starch, protein, and polymer like rubber, nylon, etc. Associated colloids are formed by aggregation of a large number of ions in concentrated solution. Example soap soil. Number 2 point. Multimolecular colloids molecular masses are not very high. Macromolecular colloids have high molecular masses. Associated colloids have molecular masses are generally high. Number 3. Multimolecular colloids atom or molecules are held together by weak van der Waals forces. Macromolecular colloids, due to long chain, the van der Waals force of attraction holding them are comparatively stronger. In associated colloids, higher is the concentration, greater the van der Waals force. Multimolecular colloids are usually have lyophilic character. Macromolecular colloids have lyophobic character. Associated colloid molecules contain both lyophilic and lyophobic groups. Preparation of colloidal solutions. As discussed earlier, the lyophobic salts cannot be prepared directly by mixing the substance with the dispersed medium. For example, colloid salts of starch, gelatin, gums, Arabic soaps, etc. are prepared by simply dissolving these substances in warm water. Similarly, a colloidal sol of cellulose nitrate is obtained by dissolving it in an organic solvent such as ethyl alcohol. The product obtained is called collodion. However, the lyophobic salts cannot be prepared easily, hence the following two types of method are employed by obtaining lyophobic salts. Dispersion or disintegration method. These methods involve the breaking of bigger particle to colloidal size. The methods generally employed for the purpose are described below. Number 1. Mechanical disintegration. The mechanical disintegration is carried out in a machine called colloid mill. It consists of two steel discs with a little gap in between the capable of rotating in the opposite direction at high speed. A suspension of substance in water is introduced into the mill. The size of suspension particle is reduced to the colloidal size. Electro disintegration Bridges method. This method is employed for obtaining colloidal solution of metals like gold, silver, platinum, etc. An electrical arc is set up between two metallic electrodes suspended in a tub of water. The intense heat of the arc converts the metal into vapors which are condensed immediately in the ice cold water bath, resulting in the formation of particles of colloidal size. Number 3. Peptidation. Peptidation is a process of passing of a precipitate into colloidal particle on adding suitable electrolyte. The electrolyte added is called peptidizing agent. A few examples solved by peptidization are given below. Number 1. A reddish brown colored colloidal solution is obtained by adding small quantity of ferric chloride solution to the freshly precipitated ferric hydroxide. Number 2. A precipitate of silver iodide can be peptized by shaking with a dilute solution of silver nitrate or Ki. On adding insufficient quantity of very dilute HCl solution to the freshly precipitated aluminium hydroxide, a sol of aluminium hydroxide is obtained. Case of peptidation. As the electrolyte is added to a freshly precipitated substance, the particle of precipitate absorb one particular type of ion of the electrolyte and get dispersed due to the electrostatic repulsion. This gives the particle of colloidal size. Freshly prepared precipitate are preferred as they are peptized. B. Condensation or aggregation methods. These methods involve the joining together of a large number of smaller particles to form particles of colloidal size. The method generally employed for the purpose. Number 1. By chemical reaction. Number 1. By double decomposition, when H2S is passed through a dilute solution of arenous oxide in water, a colloidal solution of arenous sulfide is obtained. Reaction: AS2O3 plus 3H2S. It gives AS2S3 colloidal solution plus 3H2. Number 2. By reduction. Gold, silver, platinum are obtained in colloidal form by reduction of very dilute solution of their salts with a suitable reducing agent. 2AuCl3 plus 3SnCl2. It gives 2Au gold sol plus 3SnCl4. Gold sol can be obtained by reduction of AuCl3 solution with formaldehyde and tannic acid or with hydrazine. AuCl3 plus 3HCHO plus 3H2. It gives 2Au plus 3HCOOH plus 6HCl or 4AuCl3 plus 3NH2NH2 hydrazine. It gives 4Au plus 3N2 plus 12HCl. 3. By oxidation. Sulfur is obtained in the colloidal form when H2S is bubbled through the solution of an oxidizing agent like nitric acid, bromine water, etc. H2S plus Br2, it gives S plus 2HBr. H2S plus 2HNO3, it gives 2H2O plus 2NO2 plus S. By hydrolysis method, FeOH3 and AlOH twice 3 salts are obtained by boiling solution of their corresponding chlorides. FeCl3 plus 3H2O, it gives FeOH3 plus 3HCl. OH whole 3 plus 3HCl. 2. By exchange of solvents, substances like sulfur and phosphorus are fairly soluble in alcohol but less soluble in water. If their alcoholic solution are poured in water, colloidal solution of sulfur and phosphorus are obtained. 3. By condensing vapor of a substance into solvent, colloidal solution of sulfur and mercury in water are prepared by passing their vapor in cold water containing a little stabilizing agent like ammonium nitrate. By excessive cooling, colloidal solution of ice is an organic solvent like ether is obtained by freezing of a mixture of the solvent and water. Purification of colloidal solutions.